Okay, so we'll start to model the generators. This section is going to cover synchronous machine modeling, and we will first develop the most detailed, the most accurate models for synchronous generators or synchronous machines. Then we'll gradually simplify the model until developing a number of a simplified model. So the simplest model for a synchronous generator will be the swing equation, which only have two differential equations about rotor angle and rotor speed. But the first model we're going to develop will be very detailed. It include like flux linkage, include different time scales of dynamics. So this session will cover the materials from Kunder's chapters 3 to 5. So that's chapter number 8. I strongly recommend everyone read through Kunder's book from chapter 3 to 5. I'm not going to cover every page, but I only just capture the most important material for you to be able to develop the generator model on your own and gradually simplify the model until the swing equation. And if you want to do the stability study, which need generators model, you know which model at which level of details will be important to you study. Okay, so that's our goal. Let's talk about the two types of synchronous machines or synchronous generators. So the first type is called ceiling pole rotor generator on the left-hand side, and the second one is called the round rotor generator on the right-hand side. And you can tell the difference between the shapes of the rotor. If we take a look at the cross-sectional area of the rotor, and for the first type, there's an obvious air gap between the rotor and the stator. So outside, you see there's a ring outside, which actually the stator, which means they don't, they have 3 windings, they have A, B, and C. So the convention here is if we use A, which means the current will come out from A, and there's an opposite, in the opposite position, there's an A prime, which indicates the current going into that point, okay? And the B will be lagging A by 120 degrees. So if we here, we assume the rotor will revolve counterclockwise, so it will, so the magnetic field, which is from S to N, will face A first. Then after 120 degrees, it will face B, then will face C. Okay, so the layout of the 3 winding will be A, B, and C by 120 degrees. So the stator windings are exactly the same for the ceiling pole rotor generators and round rotor generator. But for the rotor will be revolving inside of stator, and it has a very small air gap between, for instance, at this position between the N and A, but in the perpendicular direction, it will have much larger air gap. So definitely, this is just a very figures showing very simplified the layout of the generator. But if you are able to see the pictures, real picture about inside of rotor, you still can tell in which direction the air gap is bigger, which direction is smaller. So you can feel the change of the air gap due to the revolution of the rotor. But for the round rotor generator, the air gap is evenly distributed. You cannot easily tell which direction is in, which direction is, if its rotor is revolving. So all same. So the stator windings A, B, C will be connected to the external world to power the electric network and also deliver the energy to the load. The rotor will have at least one winding, which is called the field winding, to induce a magnetic field. So you see there's a wire which can induce the magnetic field from S to N. So the magnetic field can be induced by a DC circuit. If you have another DC circuit, direct current circuit, it will send the current in the same direction and to induce the constant magnetic field. The magnetic field will revolve inside of the generator, and that can induce an electric field to generate the energy. Okay, so in the modeling, we're going to model each winding, including the stator winding ABC and also field winding carrying the field current. And also we'll model some other winding which help to stabilize the generator if there's any disturbance, which are called damper winding. We'll talk about that shortly. Stator winding is also called armature winding for synchronous generators. So in order to identify the location of the rotor in the revolution, so we define the direction of the magnetic field as the direct axis, so d-axis. Okay, so which is basically in the same direction of n will be the flux leaving the magnetic, leaving the rotor. We also define another axis, which is q, which is actually quadrature axis, which is 90-degree leading the d-axis. So which means if the rotor is revolving counterclockwise, if we use maybe an angle theta to represent the position of d-axis, q will be always theta maybe plus 90 degree. So it will be 90 degree leading. If you read some textbook, especially published maybe a long time ago, some books, they use the direction lagging d-axis by 90 degree as the positive direction of the q-axis. So it doesn't matter. It doesn't. So that will introduce a negative sign for whatever we derived for the q-axis. So if we take this convention, we assume q is leading d by 90 degree. We can develop all the formulas. But if you try the older way to define q be lagging d by 90 degree, so only for some quantity in the q-axis you need to add a negative sign. But eventually, all the equations look same. Okay, so this is based on the IEEE standards. So IEEE standard recommend Q to be leading D by 90 degree. There's one consideration because later we'll assume the Q to be in parallel with imaginary axis. So we use d-axis for real axis, such as we can use a complex number to indicate any phasor quantities involving both D and Q. So if you have a phasor and the projection to the real axis, the real part will be considered in the d-axis and the imaginary part will be in the q-axis. So it's very natural to assume the imaginary axis to be 90 degree leading real. Okay, so if you take the old convention, so you have to add a negative sign. So how about the frequency of the generator? So which is equal to the number of pairs of poles multiplied by the revolution speed divided by cc. So P is the number of poles. So for these two generators, so they each generator has only one N and one S. So each one has two poles. So P will be 2. Okay. So P divided by 2 will be 1. The N here has the unit which is RPM or revolution per minute. So if the rotor is revolving at 60 hertz, which means 60 times per second, the signal speed will be 3,600 revolution per minute because it will be 60 times 60. So 3,600 revolution per minute divided by 60 will be 60. Okay, so this equation tells if P equals 2, the signal speed will be 60 if the revolution per minute is 3,600 rotor speed. But if you have more poles, you have 4 poles, still make the generator generate electricity at 60 hertz. So the N can be only half of the 3,600. Okay, so if you further increase the number of poles, the speed can be even lower. So which means the more poles, the lower speed the generator can operate in order to generate 60 hertz electricity. So let's show some pictures of the two types of the rotors, and we can explain how they are going to be utilized in the real world generators. For the ceiling pole rotors generator, so here this picture that shows a ceiling pole rotor, which has not been installed into the stator, but you can tell it has 12 poles compared to the early picture with only 2 poles. But you still can tell, obviously, the air gap will increase in some direction, right? So it's if you feed this one into stator, the air gap will not be evenly distributed. It will be the air gap will be more between any 2 poles. So for this 12-pole ceiling pole rotor generator, so if it's operated at 60 hertz to generate 60 hertz electricity, what is the speed? What is the rotor speed in revolution per minute? So because we know the frequency equals P divided by 2 times N divided by 60, right? So we can know the N will be equal to 100 F divided by P. So it's 100 times 60 divided by 12. So this one will be 600 revolution per minute. So you have to revolve at this speed in order to generate 60 hertz electricity. So if you increase the number of poles to 24, so generator can operate at even lower speed at 300 revolution per minute. So such rotors usually have a short axial length, but bigger diameter. Because ceiling pole rotor generator are typically utilized for just hydro power plant. Because when the water flows through the turbine rotor, and the speed cannot be too high. But in order to increase the frequency of the electricity also to 60, so you have to increase the number of the poles. So for the hydraulic turbines, usually they operate at a lower speed, such as 50 revolution per minute to 600 revolution per minute. So they have a large number of poles. So inside of each pole, it may have a squirrel cage winding, or number of squirrel cage windings. So such windings are called damper windings. So those damper windings are not connected to any external circuit. They're just made by some material with high resistive material. So if there's a disturbance, the rotor will be oscillating. If it's shaking, oscillating, so there will be a current induced inside of the squirrel cage windings. And because it's made by a highly resistive material, so it will generate some heat. So that heat will convert oscillatory energy into the heat. That can help damp the oscillation. So the second type is a round rotor or cylindrical rotor generator. So you can tell the rotor have much longer axial length, but smaller diameter. So if it's fed into the stator, you cannot clearly tell which direction is in, which direction is S, right? It's not very clear where are those poles. So they may have only just the 2 poles or 4 poles, depend on how the magnetic flux go through the rotor. So the air gap is almost evenly distributed within the stator. So they can operate at a much higher speed because they only have like 2 poles or 4 poles. So speed can be 1800 revolution per minute if you have 4 poles, 2N and 2S, or the 3600 revolution per minute if you only have 2 poles. For this rotor, you may not be able to integrate like squirrel cage winding, but you can design the rotor to make some area with like highly resistive material, such as there will be some eddy current induced when the rotor is shaking inside of stator. So that also gave you the damping effect. So both type of generator we're going to model the damping effect by assume some damper winding. So for the cylindrical rotor generator, you definitely can find the damper winding. There's a physical winding, but for round rotor generator, there's no such winding, but still we can model the equivalent damper winding. Yes.
While they're operating, or like would it affect like if you have a pacemaker, would it affect like a pacemaker?
So you mean a person wear the pacemaker and standing next to the? I assume so because I don't know how close you mean. Yeah, I'm not that expert. But I guess for the high voltage generators, there will be some safety concerns and for special professional people to operate. Okay. So 70% of large seamless generators on the powering the transmission grade actually run rotor generator because we know the cylindrical rotor generator are mainly used for the hydropower plant, but the hydropower plant right now only take a small percentage of the large conventional generation. But round rotor generator can be utilized as turbine generator or gas turbine, steam turbine, so they take a majority of the seamless generators. So next, we're ready to model those windings in the stator or rotor of a seamless generator. So here, so I draw a number of windings. I use letters. So each winding, I use a pair of letters to indicate. So the convention is to use the lowercase letters for stator winding, A, B, C. So for instance, this is A, and this is A prime. So which means the current will come out from A and go inside to the screen at A prime. So the axis of winding A is right now vertical. Okay, and similarly for B will be they'll have B and B prime, which is lagging A and A prime respectively by 120 degrees. So also we have a C and a C prime. So those three winding will be for the stators. Okay, and on the rotors, I also draw a number of letters and a pair of letters, but they're all capital. So that's a convention I adopt in this class. So you see there are some letters F, D, and Q, and G. I will explain them shortly. Okay. So right now I intended just to draw the rotor actually separate from the vertical axis by theta angle. The theta just indicate the location of the rotor. So that is the location of the D axis. So if we use the angle to categorize the direction of D, so the angle is theta. And the Q is the leading D by 90 degree. So that is based on the IEEE standard. So Q will be theta plus 90 degree for the angle. Okay, so for the rotor winding, we first need to model the field winding. The field winding will be, if we put so we use capital F. So we use capital F and capital F prime. So this axis is the same as the axis as we mentioned, right? Because D is define the direction of the magnetic field. So we also need to model the damper winding. So if this is the cylindrical rotor generator, so within each pole, it has two poles, right? Within each pole, we need to have a damper winding. So we'll have a Q and the Q prime in the damper winding. And also, we may also add another damper winding in the D axis, which is D and the D prime. So capital D and capital D prime, this damper winding is in the same direction as the field winding. So that's why we use the letter D. And the capital Q is a damper winding in the same direction of Q axis. That's why we use letter Q. So if it's a cylindrical rotor generator, we need three stator winding ABC, and we need three field winding. We need one field winding and two damper winding, right? So totally we have a 6 winding. But if we want to model round rotor generator, for symmetry, it's better to have 2 windings in each axis. So for the rotor, we have D and Q. So D axis, we have 2 windings. Q axis, we also have 2 windings. For D axis, we already have the capital D and the capital F. So for the Q axis, we have capital Q. Then we add another one. We call it the capital G. So capital G is also a damper winding, but which is in the Q axis. In some textbooks, just call it maybe Q1, Q2. But here, I just use the letter G. Just make it be simple. Any question here? Okay, so just summarize how many windings we need to model in the following. If it's a cylindrical rotor generator, we have 3 stator windings, which are A, B, and C. And we have 3 rotor windings, including F in the D axis, D in the D axis, and Q in the Q axis. For round rotor generator, for the rotor, we need to add a second damper winding just to make 2 damper windings in each axis. So those assumptions are usually considered the minimal number of windings you need to model. Actually, you may ask, what if my generator has many damper windings? Can I model each damper winding individual? Definitely, you can keep adding later, right? You have few windings, and for damper winding, you can have D1, D2, D3, D4. They're all in D axis. You also can have Q1, Q2, Q3, Q4, all in the Q axis. That's up to you. So later, when we develop the model, we can tell you also add more damper winding, what we need to do. It's pretty straightforward. But right now, let's just assume the minimal requirement for cylindrical rotor generator and round rotor generator. Okay. Any question? So let's talk more about the rotor position theta. The theta, as I said, is the angle separation between the Q axis and the vertical axis for this case. For this case, we assume the vertical axis is actually same as the axis of A. Because the A, B, C, they don't move. So this vertical axis will be staying there forever. But the rotor will be revolving. When the rotor is revolving at 60 Hertz, so the theta will increase at even speed, at constant speed, counterclockwise. So theta will be a function of time, will keep increasing. But it's not very convenient to categorize the position of rotor, because in reality, nobody can look inside of the rotor to see where the DS is really facing. And that's not important at all, because in reality, as I said in the last section, if we talk about the rotor angle stability, it's important to have 2 rotational masses, which means 2 singular generators. And if the 2 angles are always pointing to the same direction, the 2 generators are synchronized perfectly. But if one angle is separating from the other, the angle keep increasing, the generator, one generator may become unstable. So that means when we study the stability of singular generator, we only care about the angle of each generator relative to some reference frame. So that reference frame can be the rotor of one generator, just one generator, or could be some common reference, like average position of all the rotor. Okay, so it's more convenient we just define a reference frame. So this reference frame is like some fictitious generator that will never lose stability. Okay, they always operate at perfectly 60 Hertz. Then we can compare the rotor position of this generator versus that fictitious generator, that reference frame. So we just assume that reference frame operate at like a speed omega r. Okay, then we can introduce a new variable. This new variable really tell the relative position to the reference frame. So it's not theta. Theta is function of time that keep growing because the rotor will always revolving counterclockwise. So theta will never decrease. It will keep increasing at about 60 Hertz. But the delta is the angle relative to a frame operating at about 60 Hertz, right? So delta can be positive or negative. So if it's faster than the reference frame, the delta will be positive. If it's slower than the frame, it will be negative. So that is can indicate the real state of the generator in terms of the rotor angle stability. So based on the attribute standard, usually we use the Q axis to define the delta. So delta for this case will be theta minus omega RT. So this will tell you the direction. So this first item, the theta minus omega RT, will tell you the direction of the D axis. Then plus 90 degree will tell you the direction of the Q. Okay. So if theta is operating, the rotor is revolving at exactly this speed. This will be canceled by the negative omega RT. So delta will be constantly 90 degree. So which means the delta will be constant. It doesn't change. But if the theta is changing at a lower speed, the delta will decrease. If theta is increasing at higher speed, delta will increase. So delta is called the rotor angle. So when we talk about rotor angle stability, we mean the stability of this delta, okay, relative to the reference frame. Any question? Okay, so next we're ready to put some equations to model the voltage and the flux of all the windings. So we use cylindrical rotor generator as one example. So we only have 6 winding total. We have 3 stator winding A, B, and C. We have 3 the rotor winding capital F, capital D, and capital Q. So the main objective of the modeling for seamless machines is to find the minimal set of constant parameters by which the voltage and flux equation are in the simplest form to meet the desired accuracy. So I put this sentence just tell you when you do some study, try to find out the model, or you are modeling something. So what is the goal of modeling? Definitely the modeling is, the goal will be to identify a number of equations. So the equation you can develop your code, right? Simulation code, and to do the study. But by different method, you can have different set of equations. Some model will be more complex, will have many equations. Some model will have a fewer equations. But it doesn't mean the more equations or more parameter will give you better accuracy. Okay, so if we want to achieve the same accuracy, the quality of the model depends on the smallest set of parameters you can utilize to categorize those equations. So our goal is to find the minimal set of constant parameters. So those parameters are better to be constant, because once we define the number of parameters and also identify the value of each parameter, we can pass the values to others. So they can use the same set of value to do the study. That is about same model. So that is actually the true meaning of model. The model is assumed there's a number of equations which is actually structure of the equation. Then I need to identify the value of all the parameters. Then I can safely pass the parameter to some other student or people, and they can apply the parameter on the same set of equations. They can do a study. That's still about the same thing. Okay. And it will be important to make all the parameters to be constant. You don't want any parameter which will be a time function, will be changing with time. Then that's not a good model. It definitely to be constant value. And also we don't want to have so many parameters, because there could be possible some parameter not independent from others. We only want to find the minimal set of independent constant parameters. So to write down the equations may be easier, but to find a good set of equations with a minimal set of constant parameter, that may need to take some effort. We're going to use the following slide to demonstrate how to find the good model for the seamless generators. Okay, so to model those windings, if we treat the stator windings and rotor winding are stationary. Okay, they don't move at all. We can borrow some idea from transformers, right? For two winding transformer, you just have one primary winding, one secondary winding, the two winding are coupled. They're not electrically connected, but they are coupled through the electromagnetic field. And when we have one side to be source, the other side can power some load. So energy will deliver from one side to the other side. You can definitely have like 3 winding transformer. You can also borrow the same idea. But for transformer, all the winding are stationary, which means if they face there, they never move. So their coupling between the two winding will be same, will be constant. Okay, so here we can borrow the idea. So now we just on the stator side, we have 3 winding A, B, C. So they connected at the neutral point. So that neutral point will be connected to the ground. So if there's no imbalance between the 3 phases, the neutral current will be 0. Okay, but if there's any short circuit on one line, so there will be some imbalance among the 3 phases, and there will be neutral current. On the rotor side, we have 3 individual windings, so they are not connected with each other at all. So we have a field winding, which is powered by a DC source. We call it EF. And we also have a damper winding. We just copy the structure of field winding. We also assume there's a source, right? It's a DC circuit, but the DC voltage is 0 because there's no internal source at all. So you can just ignore it, but we can just borrow the same structure. So here I intentionally to draw the winding of F and winding of capital D in the same direction because they're both in the D axis. And for the second damper winding, the Q axis, I intentionally to draw it perpendicular to the F and D because that winding is orthogonal to the field winding. It's with a Q axis. Okay, so next I need to assume some direction of the current and flux linkage. So on the rotor winding, on any of the rotor winding, the winding is considered a load of the circuit. So for instance, in the field winding, so this winding is powered by the DC source. So if it's a load of the circuit, I need to consider the current to have positive direction same as the flux linkage. Because the flux linkage divided by the current will be the L, will be inductance. So that should be positive, okay? But if we'll talk about, if we talk about any stator winding, so that flux linkage will be the source of the electricity. So I need to make the current be opposite, in the opposite direction compared to the direction of the flux linkage. Because if this flux linkage increase, the current will increase, will generate the current going outside of the terminal A for this case. Okay, so that's what I assume because any winding in the rotor will be the load of that circuit. Any winding in the stator, in any stator winding will be the source of that circuit. So the current for the stator winding will be opposite to the positive direction of flux linkage. Okay, so now we're ready to start writing the equation, similar to the way we use for the transformer circuit. So for the field winding, the source will be the DC source to generate the field current, which is EF, which is equal to the voltage drop on the resistance with the field winding, because we assume the field winding is not like superconductor, so it will have some resistance. So the voltage drop on the resistance, then voltage drop on this winding. So it'll be equal to the derivative of this flux linkage with respect to time. If we pick the winding A, okay, so the source is actually the flux linkage. So be this one to induce electricity, and that one will generate voltage drop. First on the resistance, then on the EA. EA is actually treated as load, which is the voltage as added to the external world. So if you want to, maybe we can write equation this way. So this is the source on the stator winding. And on the right-hand side, there will be a voltage drop, the first on the resistance, then on the load, right? So that is same equation here. If we move the RAI to the left-hand side, so that's the same. So if you compare this equation to the voltage equation for the field winding, so basically look very similar, but the current, as I said, because current take opposite direction to the flat linkage, so there will be a negative sign. There will be a negative sign with any current on the stator winding. So you can definitely write down the equation for like a D winding, capital D, capital Q, and for B and C. So they will be same. You just change the letter. You just change F to D or change F to Q. That will give you the equation for another two rotor windings. And similarly, you can replace A by B and C. Okay, for the flux linkage, the flux linkage in winding F, that is contributed by all currents. Okay, so each current is just a linear combination of many atoms, right? Each atom will be one current multiplied by a mutual inductance. Okay, so because for this one we want to calculate the flux linkage to contribute in the winding F. So each atom will be some mutual inductance with one subscript, which is capital F, and the second subscript will be from either A, B, C, or F, D, Q. Okay, and then the current will be the same current in that winding. But because here we have stator winding, rotor winding in the opposite direction, so for the first group, which is for the stator winding, they will have negative sign because stator current is opposite to the flux linkage. Is this clear? Okay. Similarly, if we calculate flux linkage for any stator winding, that also linear combination of like just summation of many atoms of the mutual inductance multiplied by the current. So the first subscript is still A, and the second will be either ABC or FDQ. If the second is same as A, which means this is like a self-inductance. If it's different from A, it will be a mutual inductance. So mutual inductance can be the mutual inductance coupling the A winding versus another stator winding or maybe another rotor winding. If it's stator winding, you need to add a negative sign. That is only because of the stator current take the opposite direction. Okay, to summarize, we have so many parameters, right, to model this generator, so which are basically those self mutual inductances, which are such as L with two letters. So the two letters categorize which two windings we're talking about. If it's about rotor, so it will have rotor self inductances. So the two letters are identical. So LFF, LDD, and FQQ. If the two letters are different, FD, DQ, FQ, which means rotor mutual inductances. So for instance, L capital FD, which means mutual inductances due to the current in the field winding, and also the DS is damper winding. Okay. All right, so for the self mutual inductances with the rotor stator, we also have a lot of L's. So each L have two letters, two subscripts, and they're both lower cases. Okay, so the letter indicate they are either self inductances or mutual inductances. Like LAA means the self inductance with winding A. LAB means mutual inductance between winding A and winding B. So lastly, we have stator to rotor mutual inductances. So also each L has two subscript, and first one from a stator winding, second one from a rotor winding. So those are all the combination we have. Yes. So now we can put all the equation into this matrix representation, right? We make the left-hand side of the equation, we have a column on all the instantaneous voltage. We have EA, EB, EC, and then EF, ED, EQ. Definitely ED and EQ are 0 because there's no internal source. Only EF is equal to the DC voltage of the field winding circuit. And on the right-hand side, we have two items. The first item is a diagonal matrix about all the resistances of the six windings. So they are multiplied by a column of current. And in this column, so the stator current has negative sign because we define the opposite direction, and plus the time derivative of flux linkages of all windings. You can also write this equation in this matrix form. So by using this block matrix representation to make it simpler. Then second, from the flux linkage equation, the left-hand side, we have one column of all six flux linkages, and right-hand side, we have self-mutual inductance matrix. So they have many elements. So each element will be either mutual inductance or self-inductance, depending on whether two letters are same or different, multiplied by this the column vector of the current. Okay, so this is our first model of a signal generator, a ceiling pole rotor generator. But if I ask, is this a good model? It's not a good model. Why? Because although they can give you a set of equations you can calculate, solve to simulate the behavior of generator, but all there are so many parameters, right? So in the first equation, the only parameter will be the resistance matrix. The resistance of each winding can be constant. So that's constant diagonal matrix. But in the second equation, the flux linkage equation, they involve a lot of self-mutual inductances. So question will be, are those inductances constant or not? If they're constant, that's good. So we can, for each generator, we estimate the value of those inductances. We can pass the value to others for study. But if they are not constant, this is not good model. Okay, we definitely don't want those values to change with time. Okay, so next we are going to figure out whether those inductances will change with time. Okay, so here we assume the rotor will revolve at theta angle. Okay, theta is a function of time. To evaluate each self-mutual inductance, we need to find the formula to calculate the inductance. So usually the formula depends on the number of turns of the two windings, right, contributing to this inductance, and also another parameter which is called permeance, which indicate how easily the magnetic field can link the two windings. So no matter, because here each inductance involves two windings. The two windings can be same. If it's same, it means a self-inductance. If it's different, it means mutual inductances. So on the left-hand side, we just draw a figure. We assume there's two windings. Okay, the first one you have number of NS turns. The second one you have NY turns. So two numbers can be different. And so the magnetic field is revolving. Okay, changing with theta is different from from transformer. So if we're talking about transformer, the magnetic field will be there. It doesn't move. But for the generator, the magnetic field will revolve with rotor as function of time or theta. And for the two windings, depend on where they are. If the two windings are both with stator, maybe the winding X is A, winding Y will be B, so they don't change. They will stay there. Only the rotor will revolve. But if one winding is A, the other one is F, F will be will stay on the rotor, will revolve together with rotor. Okay, if both X and Y are rotor winding, maybe X is the damper winding DSCs and Y is the field winding, so they will revolve together. So then they will generate all the combinations in this inductance matrix. So we just need to figure out how those L values will change with theta. So this is the equation to calculate the mutual self-inductances. So each inductance involves the product of the two numbers of turns, ns times ny, then multiplied by this PSY. PSY is called the permeance of a mutual flux path. That mainly just indicate how easily the magnetic field can be built up connecting those two windings. So the permeance is similar to the conductance of the electric circuit. So in the electric circuit, if you calculate the 1 over resistance, so that's called the conductance. So that evaluates how easily the electric field can be built out. But in the magnetic circuit, we have similar concept, which is called the permeance. So if connecting the two windings is a completely magnetic material, which means the permeance is very large. Okay, but if it's a huge air gap between the two windings or completely air gap, the permeance will be small. So basically, permeance will change with air gap. The bigger air gap, the smaller permeance. Okay. Let's first take a look at the stator self mutual inductance. So we're talking about the this block, the green block. Okay, so here all the subscripts are from A, B, and C. So if it's self-inductance, it will be something like LA. If it's mutual, it will be like LAB. So now the two windings are both from stationary winding, which means the NX and NY, they don't change, they stay there. Okay, so their coupling will be same, will be constant. So the product of the NX and Y will be constant. So here, because we have to consider the winding can revolve, so we have to treat each of NX and Y as some vector. So not only just number of turns, also depend on the direction, the axis, how the axis face each other. So if those both are facing to the same direction, so their product will be simply just product of their number. So if it's separated by a certain angle, which is like dot product of the number and also multiplied by cosine of that angle. But for two stator winding, this product will be constant. But the permeance will be changing. Why? Because in this direction, the permeance will be largest. But if you start revolving at perpendicular direction, the permeance will be smallest. You have largest air gap. So if the rotor is revolved to this direction, the air gap will be much bigger, right? The permeance will become smallest. And when the rotor revolves by another 90 degree, the permeance will reach a maximum value again. So which means the permeance will change with theta at the period of 180 degree. So every 180 degree, the permeance reach a maximum value. So we can use a periodic function such as a sine and cosine function to model the change of the permeance. So which will be this function. So the 2 here, cosine 2 times the theta plus certain initial phase. Alpha indicates some initial phase. 2 here, it just make the period to be 180 degree, not 360 degree. And also there's some constant atom at the beginning, so just which indicate the leakage flux, the inductance due to the leakage flux. So we'll take this structure to model the self-mutual inductances involving the two stator windings. Any question? Doctor, anyone follow this approach? Okay. So next we'll move to the stator to rotor mutual inductances. So such as LAF, A is from the stator winding A, and F from the field winding. So for this case, So one winding will be the stator, and the other will be rotor. So which is like the second winding will be stay on side of the rotor. Okay, so if it's a field winding, it will be stay together with the rotor. So if it revolve, this rotor winding will revolve together with rotor. And if the generator is properly designed, so the stator winding can be evenly distributed inside of the stator. So that makes the air gap to be constant. So now the air gap, to influence the permeance will be the air gap between the rotor and the stator winding. So that one can be constant. So for this case, the permeance will be almost constant if the generator is well designed. But the coupling between the two winding will change as periodic function of theta with period of 360 degree. So for instance, in this direction, the two winding will be in parallel, okay? But if the other one is revolved, after 360 degrees, they will come back to the same direction. After 180 degrees, they are pointing to opposite direction. So there will be their inner product will introduce a negative sign. So this one will the coupling of two winding will have a period of 360 degrees. So this one can be modeled by a cosine function, and the beta here is just an initial phase. So finally, if we consider mutual self-inductance of a rotor windings, they're all constant, okay? Because first of all, the two winding, they both stay on the rotor. So their coupling never change. For instance, the field winding and damper winding D, they're always in parallel, okay? So N times N will be constant. Also, the air gap seen from the rotor will be same, no matter how the rotor revolves inside of stator. So they are all constant. So this is just a quick analysis on how those L can change with theta. So conclusion is everything here, they are all constant, okay? They're constant. Anything in the green box, that will change as 180 degree as period. Anything in those gray bars will change as 360 degree as period. So every 180 degree, any inductances in the green block will reach the maximum value. Every 360 degree, the inductance in the gray bars will reach the maximum value. So next, we need to figure out the accurate formula of each inductance. So for the stator self mutual inductances, okay. So here I draw the axis of A, B, and C. Those green axes, they don't change, okay. But the rotor can revolve. The rotor will revolve. At this initial time, the theta is 0, which means the N direction is in parallel with A. But when the time flies, this theta will increase, so the angle can separate. So this self-inductance LAA is equal to the ratio of the flux linkage phase A winding to the current of LA. It's basically just the flux linkage divided by the current IA. And you need to assume the current of other circuit to be 0. So we have analyzed this one from previous slides. The permeance will the maximum permeance will reach the maximum value every 180 degrees. So right now, when theta equals 0, that's maximal permeance. So when the N move here, and as it turns out by 180 degrees, so the rotor is also parallel with the A axis, so it will reach the maximum value again. Okay, so which means the LA just similarly formulated by this equation. So it has maybe a constant term plus a periodic term. The periodic term will be the cosine proportional to cosine 2 theta. So the initial phase is 0 because we assume we start from theta equals 0 when the rotor is in parallel with the a-axis. And for LBB and LCC, we just simply add a negative 120-degree phase and a positive 120-degree phase. So because B is lagging A by 120 degrees. So if this rotor revolve 120 degrees, then the LBB will reach the maximum value. Then it's a further turn by another 120 degree, LCC will reach the maximum value. So typically the constant term is bigger than the coefficient of second term. So there's more detailed discussion in the Quinter's book. So if you read the book, it tells you why it is like this. So next one, we can use the LAB as one example. So for the LAB, it's about the mutual inductance due to the currents due to the winding A and B. But because A and B is separated by more than 120 degrees, which means if the current change in the winding A, it will influence the flux linkage connecting to A and B, or influence the winding B because they separate by more than 90 degrees. So this mutual inductance cannot be positive, it will be negative. And for this case, we need to find out where the fermions will reach maximum value. So we'll reach when, if I still assume A, B, C pointing to those three directions, and when the DS is lagging A by 30 degrees, which can give you the smallest error gap connect for the flux linkage paths connecting A and B. Okay, so if you can imagine if the rotor is right at this position, the permeance will reach the minimum because you have largest error gap from A to B. Okay, so when the theta equal to either negative 30 degrees or positive 150 degrees, the permeance will reach the maximum value. So this is 150 degrees. So now we know the mutual inductance LAB will be pretty similar to the equation above, but will have a negative constant and negative this coefficient, then multiply by cosine 2 theta. And this positive 30 degrees that indicate the initial phase is negative 30 degrees. So when the theta equals negative 30 degrees, and this periodic term will reach the maximum value. And it is also equal to the LBA. We can, by adding the negative 120 degree phase and negative 240 degree phase, we can easily get another two formulas for LBC and LCA. Quinter's book explains why the mutual part, the capital MS, is about half of the self-inductance. I don't go into this detail. Okay. For any items for the rotor to stator to rotor mutual inductances, so we're talking about anything with one letter from ABC, the other second letter from FDQ. For this case, we know the period will be a 360 degree because one winding will be revolving together with rotor. So the permeance will be constant, but the coupling between the two windings will be a periodic function of theta. Okay, so we can easily write down for the DSs, for instance, LAF. So that will be proportional to a cosine theta. So if a theta is 0, this winding on the rotor will be totally coupled with that stator. Okay, so if theta is 0, and if we're talking about F winding and A winding, So the coupling between the winding F and winding F will be completely. So that will be maximal. And then we move to the next one in B. So we'll add a negative 120 degree, and C will be we'll add a negative 240 degree or positive 120 degree. So similarly, we can have those items, they'll be same. So for the Q axis, because Q is lagging D by 90 degree, okay? So if we define the leading D by 90 degree, which means if the rotor revolve counterclockwise, it will face D first, then after 90 degree, it will face Q. So you need to add negative 90 degree phase. So that will be negative sine theta. So if you define the Q axis to be leading D, to be lagging D by 90 degree, on those all tight spoke, so those negative sign will become positive sign. Yeah. Okay. I just stop here so we can continue on next Tuesday on the modeling. Okay. Yes.